Hey everyone, welcome to our final project presentation from my BITI 1113 Artificial Intelligence. I am John Quinn Chen and together with my team member Ismail Hakimi and Fahmi Iskandar. We are group 3 representing section BITC S2G2. Today we are working to you through our vision based artificial intelligence system built to solve real world electronic waste identification bottleneck using streamlined browser-based deployment pipeline. Let's look the real let's look the real world problem we are tackling here. Sorting out miscellaneous electronic device recycling facility by hand is a massive operational headache. It is incredibly slow, heavy dependent on manual human labor, and prone to sorting mistake. Right now, facility inventory tracking relies completely on hardware, barcodes, and serialization sticker. But when items arrive beat up, unbranded, or stripped of label, the tracking system breaks down. Our vision, based on classification pipeline, solve this bottleneck by letting artificial intelligence engine look directly at the unique feature of the hardware. We designed this project around specific artic- architectural goals. Our main objective was to engineer a high-performing image model that perfectly categorized three target class: keyboard, mouse, and smartphone. We also set out to implement a live web-based prototype dashboard that run instantly for an everyday user. For our system's code, we focus tightly on core desktop and mobile peripheral form factor to prevent training confusion, overlapping hardware item like laptop, charging cable, and tablets are kept strictly out of scope.
This project stands out because it aligns directly with international ecological standards and the United Nations Sustainable Development Goal 12. By automating the physical category verification step, e-waste processing centers can dramatically scale up the daily throughput volumes. Facility no longer need a highly paid computer hardware expert standing next to the sorting lines 24/7 just to identify miscellaneous peri- peripheral scrap. This optimization scales up overall resource recovery and keep toxic components safely out of local landfills.
Okay, let's look at the computer vision science running underneath this application. Image recognition tasks excel when using convolutional neural networks or CNNs. Instead of a human manually coding hard rules for every device shape, a CNN automatically maps out features like edges, textures, and geometric profiles straight from visual dataset examples. To make this run instantly on a basic web browser, uh, without crashing, our system relies on Google Teachable Machines mobile net architecture. MobileNet breaks heavy standard convolution down into depth-wise separable layers, minimizing computing costs so the model executes locally on the client interface without needing a heavy cloud database server.
This section highlights the structural solution design flow of our application data. This operational loop moves sequentially through 5 core processing stages. First, the operator places an item in front of a standard webcam or upload a raw file asset. Second, the canvas layer instantly groups and scales that frame to clean square input grid. Third, the model evaluates 2 pixel tensor against our trained parameter weights. 4. The network returns a probability distribution vector. And 5th, our front-end interface dynamically renders the final prediction to the user.
Okay, we designed this system to satisfy rigid functional and non-functional engineering requirements. Functionally, the application must process live camera feeds smoothly, read file buffers, generate class matches, and actively tally up item totals. Non-functionally, we prioritize execution speed and usability. The system keeps network inference latency under 150 milliseconds per evaluation pass to ensure a true real-time response, while presenting an accessible layout that can be controlled by warehouse staff with zero machine learning background. Moving on to our dataset preparation and machine learning setup, we collected roughly 100 high quality balanced image sample for our keyboard, mouse and phone directories. To keep our network structurally secure, we introduced a critical fourth category called non-electronic waste. This class trains our filters to recognize an empty sorting table, room background, and moving hand. This stops the AI from throwing out false guesses when the camera detects a random noise. The network optimization ran over 1,000 training epochs with a batch size of a 16 and a learning rate of 0.001 to guarantee a excellent and to guarantee an excellent parameters convergence. For our actual system implementation, we coded a fully responsive web application using JavaScript and React. We integrated Ant Design to render professional layouts and warning banners. To manage our application state data, we use Redux Toolkit, which hooks directly into our model's output vector and automatically increments a live session tracking counter whenever a device hit is confirmed. We also added client-side Z transformation calculation logic to normalize raw counts, making our data logs completely clean and ready for facility logistics software.
We stress test our completed deep learning model by passing entirely unseen images across 5 separate testing scenarios. Our data results shows that the keyboard class maintains the highest accuracy because its repeated keycap grid is incredibly easy for conventional layers to isolate. The mouse class was the most sensitive to drops in performance under the low light and clutter. This is because mouse bodies vary a lot across brands, and glossy polymer coatings cause reflection that mess with boundaries definitions. To handle this, we had coded a strict 70% confidence filter into our dashboard to block any weak guesses from corrupting our inventory total.
Betul macam tu. Okay, so right now we are going to do the physical demonstration of our teachable machine. Okay, first of all, we have 4 different classes, which is non-electronic waste, keyboard, mouse, and smartphone. So let's test them one by one. First, non-electronic waste. Show something. See, 90-ish% accuracy. Alright. So, then how about we moving on to keyboard? Okay, as you can see, the machine detects this white thing as a keyboard with a whopping 100% accuracy. Alright, flip it. See? Still detects it as a keyboard. Okay, moving on. How about mouse? Show some mouses. Same as before, it detects this white mouse as a mouse. Okay, nothing fancy. How about the black one? Okay, properly. Okay, it still detects it as a mouse. Alright. Okay, and then for the final classes, smartphone. Let's go. Smartphone. Okay, flip it, flip it, flip it. Yes, sir. Smartphone is a smartphone. How about the other one? Still smartphone. Nothing changes. Alright. Something else? Last one, last one, last one. Last one, last one. Okay, smartphone. Alright. So, all these tests shows that our teachable machine, uh, our teachable machine succeed in detecting all four classes. So that's all from us. Moving on to conclusion.
In conclusion, our intelligent electronic device classifier successfully proved that browser-based computer vision can streamline EOS sorting lines and automate basic logic logistical steps. Our current prototype is limited because a narrow class list forces the model to make a wrong guess if you show it unmapped items like a laptop or a router. Moving forward, our group plans to expand our training dataset varieties, add funny component subclasses, and integrates bounding box object localization so our app can track multiple item movings down an industrial conveyor belt at the same time. That wraps up our presentation. Thank you so much for your time, and we are happy to take any question. Thank you.
Thank
Okay,
you.
thank you.
Thank you for watching and listening.
That's all from us.
Thank you.